Hello, welcome back. Today we're going to have a lecture on sampling. The sampling method is actually really useful in many aspects, and we'll see how that works. Previously, we've seen this slide before, the exact same slide. Basically, the point of the slide is that you can, if you're trying to find the average value of something, you can either sample the entire population or you can sample a subset of the population. So if you have the whole population versus the subset of the population, the average should approximately equal to each other. And this is because, as we learn, this concept called the law of large numbers, where if you have x bar as the average and mu as the true average, so this is the approximate average and this is the true average. So therefore, the difference between them, your approximate and the true, is the error. So what the law of large numbers basically says is that the probability that the error is greater than being large, the probability of error being large approaches zero as you increase the number n, the number of sizes. And having this law of large number, it leads to a lot of implications. One of the implication is that, well, previously we saw, like, we have the data, right? And from the data, we have been trying to learn how to find P of X. So from the data, we can find P of X. And once we have P of X, we can calculate all sorts of um, statistics. One of which is we can calculate the mean. So the integral of x px, we've seen this many times in the past, as well as on your first exam. So you can find the mean, or you can find the variance, which is the average distance from the center square averaged by the probability. So we've seen that once given data, we can find P of X, and if we have P of X, we essentially can calculate this very useful statistics, such as the average distance from the center or the average itself. So that is essentially what we've done previously. And the law of large numbers also tells us that if we have the data, we don't actually need to get the P of X. Instead, if we want to find the average, why don't we just actually average the numbers together? So look at the difference. Over here is an integral. Over here is just averaging the number. And the law of large number essentially says that if we just average them, it's going to approximately equal to this integral here, right? And the same idea follows if we want to find the variance. Well, we can just average up the average distance from the center square. So if you just find the average distance from the center square, that also approximates this. This leads us to the conclusion that the mean here and the mean here, they're calculated the same thing, right? They're calculated. Therefore, this and this must approximately equal to each other. Okay, so over here, this is the integral from here, and this is equal to this. So what I'm saying is that both of them are trying to calculate mean. This is the approximation, and this is the truth, and they should approximately equal to each other. Now, the key difference here is this is an integral, and this is a summation, right? Summation is much easier than integral. So therefore we can approximate the result of an integral by averaging. And this idea extends to other things, like over here is the equation for variance, and this is the approximation of variance. Notice how this is a rather complicated integral, and this right here is just averaged. Therefore therefore it's not just finding the average of the variance. This idea extends to any function, right? This portion can be any function you want, and we can approximate this integral by simply averaging the result of the function, right? So if you have any function, f of x, p of x, dx, as long as we have samples from p of x, if we have samples from p of x, then we just plug those samples into f of xi and average them, and that they would be approximately the same. Approximately the same. This is a very, very interesting conclusion, because there are many, many integrals in life that are impossible to solve, like very, very complicated to solve. And this is essentially telling us that we don't need to solve the integral. We can get the exact, not the exact, but approximate result by averaging. Okay. So so for your first exercise, let's really confirm this. At this point, we've worked with the lunch weight data quite many times now, and you've gotten this p of x. Let's say we have this p of x, and you want to use Python. Let's use Python and just solve this integral. Actually solve the integral using Python. And then compare your result here with just averaging the number. Based on the law of large number and what we just learned, they should be approximately the same. Okay. In this next exercise, well, instead of just x, we're going to find f of x, where f of x is an actual equation, 2x plus 1. And we're trying to find this integral here. We're trying to find the integral. And based on what we just learned, this integral is approximately equal to, if you simply take the samples that from lunch wait time and plug it into this function. Remember, f of x px dx is approximately equal to 1 over n summation f of x, right? So this right here is equivalent to this. So what I'm saying is, just try it. Try to solve the integral here, and then try to solve the integral here. And you will see, you will confirm to yourself that what I'm saying is true. You can approximate a really complicated integral simply using average. Okay. I pause the video and go on and do this. I think the solution is over here. All right, so the power of using average is amazing. It's really amazing. You no longer need to solve this complicated integral. You can get approximately the same result simply by plugging the samples. Once again, the samples from this distribution. Okay, so the sample previously was our data, right? Now, here comes a question. What happens if you don't have the data? You just have this integral. You're trying to solve this integral without the data, right? Can you still solve it this way? Well, there's obviously a problem, because you need the samples from P of X to plug it in here. So if you don't have the sample, it kind of implies that if we don't have the sample, we cannot approximate this integral anymore. And the answer is no, we can actually get around that. Even if we don't have the samples, we can still approximate this. And we can do this through this concept called sampling. So previously, we know that we had data, right? And using data, we were able to generate the distribution, right? So this is from data to an equation. Now, what I'm saying is, we don't have the data. From the equation, we can generate the samples. We can generate our own samples. And once we generate our own samples, then we can plug the sample into this formulation and solve the very complex integral. Okay, so this process is called sampling. Basically, I want you to remember this picture. This is called sampling. And there, sampling itself is a gigantic field. Like you can spend a whole class just teaching different kind of sampling techniques. But we're going to start off with the most basic techniques that everybody knows in machine learning, and they are labeled in red. So the top four, these four sampling are the easiest, and then these sampling, Gibbs sampling, Metropolis. These you will probably learn in machine learning too, and these you will learn in like neural networks or something. So these are very much more advanced. So that's the idea. Now, sampling from data, what does that mean? If you take, for example, Gaussian distribution, right? Gaussian distribution, and you generate bunch of samples. So this command here in Python just generates samples for you that are Gaussian distribution with a certain mean and standard deviation. And if you just look at the 10 samples, you don't see any particular pattern, right? They're just 10 seemingly random numbers. However, if you take 1,000 samples it generated and plot out the histogram, notice how the histogram looks almost identical to the equation. And this is really, really useful that the histogram is the same. This implies that you started with this red line, which is the equation, and you generated some samples of the histogram. So you're saying the data you generated match really closely to the p of x that you came from. Okay, so this is the idea of sampling. And for the most basic equations that you've seen so far, exponential, Gaussian, Bernoulli, categorical, all of those you can essentially just call Python command to do it, like exponential, categorical, normal, uniform, Poisson. All of these you can just call it, and these are not that complicated. They're not that complicated. We're gonna what we're gonna focus more on are the non-regular distributions. What if the distribution is difficult, like something that looks like this? Can you still generate samples with a histogram that looks like this? Okay. All right. So right now, just get used to the idea of sampling by practicing sampling by generating 50,000 samples from an exponential distribution. Now the exponential was right here, right? Exponential distribution. And then identify the equation p of x, and then check if mu is equal to 3 because you generated with a mean of 3, right? So basically you start with the probability distribution with mean of 3, and then after you generate the samples, check if it is actually mean of 3, and then draw the histogram and see if it matches, right? So here's the you should draw histogram should match. Okay, now I'm going to skip the second part, just do the first part. Okay, that is our part 1.